Hello and welcome to part 2 of lecture 4 of ENGR 2301 Engineering Statics. In this video we're just going to do a quick look at how to frame and work with free body diagrams. So this is maybe something you've seen before, or may not have been, or maybe it may not have been. Let's look at free body diagrams. And I'm going to talk about this in with a focus on the course of statics. And you probably have or may have seen this before in other courses, but it's always good to have a refresher. So first of all, what is a free body diagram? Well, or what are free body diagrams? These are simple diagrams or drawings that represent all the forces on an object necessary to keep it in equilibrium. Represent an object and all the forces necessary to keep it in equilibrium. So, let's see. Ultimately, what this is a method of isolating the object. That's the key thing to keep in mind. Often we are isolating the object and replacing physical things or physical contexts or physical objects with arbitrary forces or just force labels. Often physical objects are even cut and replaced with forces. Or physical connections are even cut and replaced with labeled forces. And replaced with labeled forces. So let's talk about what a free body diagram should have. There are a few things I think every free body diagram should have. So let's get this. Things or necessities or needed things for free body diagrams. And I may just abbreviate these FBDs. First of all, I would mention that they should have a quick sketch or drawing of the object itself. Not necessarily always important, depending on what type of system you're doing or what type of thing you're working with. This does not have to be anything demonstrating great art skill, but it can be useful sometimes. And this is doubly important, or especially important, if there is any kind of dimensions that we need to worry about, or where the shape of the object actually matters. So in this lecture, in this unit here, we're looking at point particles, so the actual dimensions of the object in question don't really matter, but later when we get onto more equilibrium of rigid bodies, then that will become more important. 2. All the forces necessary to hold it in equilibrium. In equilibrium. Now, this may entail cutting through existing or real objects, or may entail cutting through an object to reveal a hidden internal force. And maybe I can illustrate this, what I mean by this, through drawing. An object to reveal internal forces. So, for example, if you remember back to a previous example we worked with, where we had the 3-rope system, we modeled or we calculated the equilibrium of this, or the forces in this, by isolating this middle joint here. There was a weight here. And notice I made a little, let me do that in a different color so it's clear I'm talking about maybe a zone of analysis or something. And notice we basically cut out that point here. And I was essentially looking at that little region right there, and every time my little circle crossed over a boundary, that revealed a tension force. So I had that point, and those three forces, or those three cables, were replaced with equivalent forces. The T1, the T2, and the T3. And the T3. And I think I may have labeled those slightly differently in that video. But anyway, and this really illustrates what I think a free body diagram really is. Like, imagine I could, okay, for example, imagine I had a magic wand, and I could, okay, so imagine I had a magic wand, and I could go up and, let's say I have my little magic wand here, a crudely rendered magic wand at best. And let's say I could do some Harry Potter faux Latin spell, and based on where I was pointing it, and okay, this would be great. I would like position this thing anywhere I want in space, or just in a room or whatever, and depending on what angle I put it at, and maybe I could say some number of newtons in Latin or something like that, and it would magically out of nowhere apply a force vector to an object. Like, I could, you know, apply a 10 Newton force at an angle of whatever I hold the stupid magic wand at, and that object that I pointed at will just magically start moving at a certain, or reacting, or moving or reacting at that certain force, and at that certain angle. So that's kind of how I perceive free body diagrams. I know that's kind of weird, but it's kind of, the way I kind of perceive them is, if I had this magic wand that could just arbitrarily apply forces at any of any magnitude and of any kind of direction I wanted, if I could just or if I could snap my fingers and create a force out of nothing, what kind of forces, or what would I have to do to keep an object at the location it currently is? In other words, that little particle here, if I had this magic wand, what would I have to do with it if I literally cut it out? So if I could magically apply forces, I could come along and I could physically cut this rope here and apply an equivalent force there. I could use the magic wand, line it up just right, and tell it, okay, I want this many newtons in this direction, and it would, I could physically cut the wire, and it would still remain in place. And in the end, I would have, the same thing with this bottom one, and in the end, I would have this little bit of wire that was held up with nothing than the three mystical magical forces that I created with my literal magical wand. Now, that's a bit absurd, but it does reveal what I really think a free body diagram is supposed to illustrate. It's supposed to illustrate that if I could just magically create forces out of nothing, not going through a rope or a surface or an electric field or anything like that, literally forces from nowhere, if I could do that, what kind of magical forces would I need to apply to an object in order to keep it in the same position it currently is? And that's really what we're drawing with a free body diagram. We're saying, okay, if I could get forces from nothing, ignoring let's remove all of the actual physical supports on an object. Let's ignore all the forces. Sorry, not all the forces. Let's ignore all the contacts, ignore electric fields, magnetic fields, gravity, whatever. If I can just remove all of that and replace them with pure, pure magical forces almost, what would I need? What would those forces need to be? And I have to say magical because there is nothing in the universe that can create a force from nothing. Every force has to be created from something. Even something that can act at a great distance, like gravity. That's still from the combined effect of mass. It's gravity. Electric fields, those can act over some distance, but those are not literally magical. I'm talking about something, when I say a magical force, I'm talking about something that I could just arbitrarily snap my fingers and nothing else created it. It just is there via, divine intervention. It's there now. So what would I need to do? What kind of forces from nowhere would I need to apply to an object at those same directions in order to have it maintain its current position? And the reason why those are important, and obviously in the real world we don't have magical force creating magic wands, but by doing this kind of analysis, we can find what kind of forces exist in real objects. And sure, there are ways of directly measuring force in objects, such as force gauges and strain gauges and things like that, but most objects don't come pre-wired with force gauges and strain gauges, and often it'll be cumbersome to do so for most common structures and making machines and things like that for our mechanical engineering friends. And so often it's beneficial to model things this way. Anyway, that's definitely a tangent. So all the forces necessary to hold the object in equilibrium. 3, let's see. I would say, also note on the forces, sorry. I should say that these are any relevant forces, any forces that are going to be substantial. For example, now obviously I can talk about things like really, really tiny things, like if I'm sitting here, I'm sitting in a room right now recording this lecture, and I'm sitting in a chair, and the relevant forces on me are gravity and the normal force exerted upward from the chair. But just like we talked about when we looked at our earliest discussion in Lecture 1 of scientific models or engineering models, there are an infinite number of possible forces that we can include in any kind of analysis, or in turn, any kind of free body diagram. I could start modeling really ridiculous things like the gravity exerted on me by Alpha Centauri, which is the nearest star to the Earth, but if you actually calculate that, that is so ridiculously small it's not worth considering. Now, that's a trivial one, and is basically irrelevant to any kind of engineering anywhere on the Earth's surface, but there are some forces that are irrelevant depending on context. So that's really depends on what kind of engineering you're doing. So for example, right now I'm sitting in my chair. So I'm sitting in a chair right now. Here's the chair, a very crudely rendered chair, and here's me, very crudely rendered me, writing on a little tablet here. Now, again, the significant forces are the normal force. The significant forces are gravity, my weight, and an equal and opposite normal force acting upward. An equal and opposite normal force acting upward. Those are the two main forces acting upon me right at this instant. But they are not they are not the only forces. And they are not, and when I say they're not the only forces, they're not the only forces that would never be important to any kind of engineering. So, yes, we can easily dismiss the gravity of Mars and the gravity of the moon and things like that, because there is no engineer that needs to consider those unless you're literally working for NASA, or I guess Elon Musk nowadays, designing some sort of rocket that's going to go to Mars or something like that. But any kind of earthbound engineering, those weird things like that you don't need to worry about. But there are many things that engineers actually do have to worry about, depending on context, that are not important here. So for example, the chair that I'm sitting on is reasonably level. It's reasonably level, so I can assume that it's not tilted at a sphere angle. However, what if the chair I was sitting in, for whatever reason, was a really weirdly built chair? And what if, for some strange reason, I like sitting in a chair that was built like this, and the seat I was sitting in was at some crazy angle? I don't know why you would sit in such a chair. Maybe some doctor or something could convince me that there's some health benefit to half standing up and sitting. I know there's some people like to use standing desks, so maybe somebody could argue somehow that this half standing position is beneficial. I don't know. I'm not a doctor or a medical person whatsoever. So, anyway. But let's say for whatever reason I was sitting in this weird chair with a seat at a 45-degree angle. Well, in that case, there would be a different force that would actually be very substantial acting on me. I would have my normal force, but for one, that normal force would be perpendicular to the surface, and I would have my weight still acting downward, but in turn, friction would become substantial. A force of static friction would become substantial, because here there are no significant horizontal forces present. Here, just the fact that I have my weight being not directly aligned with the surface, directly perpendicular to the surface, my weight is going to produce some tendency to slide down that ramp. So I would need some sort of frictional force to resist that. So, again, context dependent, and the context makes this force makes the frictional force important. Now, the reason I'm mentioning this is that even this chair that is that I've modeled here, that I can consider horizontal, truth be told, it's not perfectly horizontal. It is absolutely impossible in the real universe to build anything that is perfectly horizontal. So, truth be told, there is some non-zero frictional force that is keeping me sitting in this chair. It has to be. Otherwise, unless the chair was magically perfectly horizontal, I would slide off of that. And that's ignoring the fact that I am always leaning to some degree and I need some friction to maintain my position. Also, other forces that are negligible, a big one that comes to mind is actually a big one that comes to mind is buoyancy. When you learn, if you study fluid mechanics at all, you know that at any time, an object immersed in a fluid experiences a buoyant force. And if I am floating in the water, that force becomes substantial. If I'm in a boat, that force is substantial. I am standing right, or I guess I'm sitting right now, where I'm positioned physically right now, I am in a fluid. I am in air. If I wasn't in air, you would know very quickly, one, for two reasons. One, because I would be dead, and two, because you wouldn't be able, this microphone that I'm speaking into would not be able to detect any sound waves because there would be no air for my lungs to create sound waves and for the microphone to pick up. So, the buoyant force on an object is equal to the weight of the fluid I displace. My body, like every other object, takes up non-zero volume. And so I displace a tiny amount of air. And so again, I do displace a tiny amount of air. And if you measured it, I would actually produce a small buoyant force, or the air around me would produce a small upward buoyant force on me. Now, that buoyant force is nowhere near enough to actually levitate me or elevate me above the Earth's surface, and not really worth considering in any kind of real analysis. But it could be important if I was in a different fluid, for example, floating on water. So again, the forces that you include are extremely context dependent. You can't just say, oh, here are 10 forces, these are the 10 forces you'll ever need to worry about. Obviously, the gravity of, Ceres or the gravity of Alpha Centauri don't need to be included. So, but as long as you include these 10, you're good. No. It is context dependent. It is extremely dependent on what kind of system you have, the situation of it, the layout of the geometry, etc. And you as a practicing engineer, you need to be aware of that. Okay, with that spiel out of the way, let's move on to the next item. That would be relevant dimensions, or important dimensions. So important dimensions, you really should include these if you can. So basically, my philosophy at least is, on a properly done free body diagram, someone should be able to calculate all the forces, or basically back solve the problem, using only what you put on the free body diagram. In other words, you should be assuming that the person who sees the free body diagram doesn't have the problem that you've been given in front of them. You should be able to just work off of just the free body diagram. So for example, in this case here, the relevant dimensions would be the angles, I would think. Those would most likely be the relevant angles. Or if you were given the slopes, like in the examples we worked with previously, or that one example we worked with previously, the slopes would be the relevant dimension. So they can be things like angles and slopes of forces. And when we get to things like rigid bodies, dimensions of the object do become important. So distance to forces on rigid bodies, those are extremely important because those are what we're going to need in order to calculate moment arms to forces on rigid bodies. For some sort of units would be nice, but I imagine those will mostly be included in those will mostly be included in your dimensions and your forces. And 5, I would say, probably, sorry, I'm writing this here because of this menu here. And 5, probably a coordinate system. Generally, whatever coordinate system you are using should be included here, including and this should include the direction of the axis and the origin of the individual axes and the location of the origin. So if you're going to put the zero elevation so low that everything is a positive elevation, that's fine. But that should be relatively apparent from your free body diagram. And so that really does cover the basics. Let's see here. Anything we're missing? I think that just about covers it. But that really is through most of things. So a few notes on this. Let me talk about a few common errors or common issues on free body diagrams, besides not including some of the things I suggested on free body diagrams. One might be your, let's say, normal force. I see this a lot, less so for university level students, but especially back in the days when I used to tutor a lot of high school physics and such, I had this problem all the time, and including I was once horrified when I heard a student, oh my god, I got so sad when I heard this. It was a high school student, and that high school student told me that their teacher had told them that it's called the normal force because it's always there. It's normal. I wanted to find that teacher and smack them, because that is so incredibly wrong. I just wanted to find them and shake them and say, that is not what normal force means. That is deeply wrong. You don't tell students things like that. That is so wrong. Anyway, I'm going to get off my soapbox here. So, the normal force is a contact force between bodies. It is always perpendicular to a surface. Always. And it comes right out of its name. So if you have a plane, a mathematical plane, there is a, if you remember back to your Cal 3, or if you haven't taken Cal 3 yet, that's a Calculus 3 yet, that's okay. But there is a vector that every plane in three-dimensional space that helps represent a plane in three-dimensional space, and that is your normal vector. It is perpendicular to that surface by definition in both directions. It's perpendicular. So that's what normal means. Or you probably, even if you haven't taken Cal 3, you may have seen this in other calculus courses or other math courses, because just like we have a tangent line, or if I'm going to go use an example of a curve, just like you have a tangent line that is parallel to a curve at a single point, the normal line is perpendicular to a curve at a point. This is the tangent and the normal. So normal force, again, is a contact force that is always perpendicular to a surface. So the things I've seen sometimes in students, maybe they've had some poor high school teachers, maybe they had that one high school teacher, I don't know. Sometimes you see students put things like, oh, I don't know, I get really sad when I see like an object hanging from ropes and there's a normal force on there. That makes me really sad. So the only time you'll ever see a normal force is if one object is physically in contact with another. So for example, if you have a block and a ramp, the classic grade school problem, you would have the gravity down that you often split into its parallel and perpendicular components. You might have, if this was stationary, you might have a frictional force, and you would have a normal force acting perpendicular to the surface and outward from the surface. It doesn't go, well, at least on the object in question. It's acting outward on the object, and then on the surface it would act inward. Okay, 2, pulleys. Pulleys are a common source of error. If the pulley is an ideal pulley, the key thing to remember is F in equals F out. Force in equals force out. There's a problem I've used many times on a physics, or not a physics class, on an exam, where I'll have some pulley that, it has something like this, where there is a single cable that maybe there's another pulley up on the wall here, and this rope winds around that pulley there and then connects to the center of pulley here. And these are all ideal pulleys, And the way to set that free body diagram up is basically the same tension, but a two times the tension here. And sometimes I'll see people try to do a T1, a T2, and a T3, and they don't quite realize that if it's an ideal pulley, the same force will be transferred all the way through the pulley, regardless of the number of loops. And then the idea was to work through the equilibrium therein. 3, I don't tend to use these a lot in my exams, but the book mentions it, so I might go ahead and mention it here. Springs. If there are any springs in your diagram, these will follow. Springs will follow the spring law. F equals kx, where k is the spring constant, which is force divided by distance. But you can read about that in your text if you wish. Okay, and that's a basic introduction to free body diagrams. I think that'll do it for part 2. And in part 3, I want to go into some examples of applying equilibrium equations to three-dimensional systems. All right, that'll do it for now. Thank you for watching. I hope to see you all soon in part 3. And as always, thank you.